again, we had T prime is equal to R T R transpose, okay? Now, the stress tensor, I mean, it's a tensor, right? So I want to look at what happens to the stress tensor under a rotation. So if I have the stress tensor and I rotate it, okay, and if I choose the rotation matrix just perfect, right? If I choose it to be just the special value, I can diagonalize the stress tensor. So another way to think of this is that, you know, I have my little cube and I sliced it. If I slice it at just the perfect angle, then I can slice it at the perfect angle such that the resulting stress tensor will just be diagonal. Everything else will be 0. Okay? The relationship between the traction and the normal vector will be such that it's just a scalar multiple. The scalar multiple of the normal gives you the traction. So in that case, they coincide. These are just the magnitude in the direction. Okay, and the sort of convention that we use here when we write it like that is that sigma 1 is greater than sigma 2 is greater than sigma 3. So that we order these precisely, and we have a name for these. They're called the principal stresses. Okay. So can anyone, you know, here I didn't say how I would choose R. Does anyone know how you would choose R? How can I choose R perfectly such that this occurs? Yeah. So I can do what's sometimes called like a spectral decomposition, right? So that's like if I have a matrix Q that consists of the eigenvectors, right? The eigenvectors of sigma, then I'll have, well, the spectral decomposition looks like this, right? So the matrix lambda is a matrix of the eigenvalues. The matrix Q is the eigenvectors of the matrix D. And so if I choose R to be the eigenvectors, then I can diagonalize it. Okay.
Sorry.
Yeah.
I didn't get why sigma 1 should be bigger than.
That's just convention. That's convention. So whenever you do this spectral decomposition, it works. Okay, let me come back to that. First, the next question is, how do you solve for the eigenvalues of a matrix? Well, specifically, how would we solve for the eigenvectors of the stress tensor, eigenvalues of the stress tensor? Right? We'd solve this equation, right? And generically, the result of this equation would be something called so if I just compute the determinant of sigma minus lambda I, I'd get something that's like lambda cubed plus some coefficient squared plus some coefficient lambda plus some term here, right? So the I1, I2, I3, they're just coefficients of this, and this is called the characteristic equation, okay? So then I would solve this cubic equation, and it would get 3 lambdas, okay? So then I can take those lambdas, so I would get lambda 1, lambda 2, lambda 3, all right? Now, if I take those lambdas and I plug them back into this equation, and I find the null space of that, well, not the determinant, but if I plug them back into this equation, where x is a vector, and I solve for x, that gives me the eigenvector. Right? Or maybe I should write it like v. So v1. So I'd get v1, and then I'd do it again. v2. v3. Right? So then if I take q is equal to v1, v2, v3, right? Then in that case, lambda would be equal to this. Okay? However, it would still work. This equation would still work. It would still give me back the stress tensor if I chose q to be v2, v1, v3, and then lambda would then be lambda 2, lambda 1, lambda 3. Right? If I then just computed this, it would still give me back the stress tensor. It doesn't matter, as long as the order of your eigenvalues correspond to the order of your eigenvectors, then it doesn't matter the order. Okay? So by convention, then, this is going back to your question. Once we solve for the eigenvalues, okay, we make this the convention. We put the largest one first, followed by the second largest by the third. And then the corresponding eigenvectors would go into the Q matrix in the same order. Okay. And as long as you do that, everything will work out. All right. So again, we have this characteristic equation. By the way, I mean, everybody knows eigenvalues and eigenvectors, right? Does anyone not know what eigenvalue and eigenvector is? Okay. You should. I mean, I would think you know. If you don't, I've got some other videos I recorded from my undergraduate geomechanics class. I can give you a refresher on that, because I'm not going to go through the details of actually solving it, right? Okay. But it turns out the I1, I2, I3 that comes in out of this characteristic equation are called the invariants of the stress tensor. And they're invariant because they're invariant to a rotation. So in other words, it doesn't matter how you rotate the stress tensor, the coefficients there, I1, I2, and I3 of the characteristic equation will always be the same. And that's a nice thing to know, because when we go on to develop constitutive models, right, we don't want our constitutive model to be variant to a rotation. Because if it is, that means to characterize it, we have to go to the lab, we have to have a sample, and we have to do a stress strain test, and then we have to rotate that sample by an infinitesimal amount and do a stress strain test, and rotate it by an infinitesimal amount and do a stress strain test. And for the rest of our lives do that. That's what we'd have to do to populate one constitutive model. Yeah. So what you prefer is to have a constitutive model, relationship between stress and strain that's related to the invariance in some way. And then if you do that, then you can have a nice, well-defined constitutive model that's doesn't matter with respect to a rotation. And so these invariants, I1, I'm not going to work through the details, I'll just tell you what they are. The invariance, I1 is the trace of the stress tensor. Or in additional notation, we write that II. And in terms of the principal stresses, the eigenvalues, it's I1 plus I2 plus I3. I2 is equal to 1/2 sigma ij sigma ij minus 1/2 I1 squared. And in terms of the principal stresses, that's minus sigma 1 sigma 2 plus sigma 1 sigma 3. So it's nice to know what they are in terms of the principal stresses, but the more useful form is just to know what it is generically from the stress tensor, because to find the principal stresses requires this eigenvalue computation. Who wants to do that at every stress integration point? Remember, I guess I haven't mentioned, I probably should have mentioned on day one. I mean, the whole point of all this, I mean, all this finite deformation stuff, you can solve so very few problems by hand. And so ultimately, this is all the theory that we're going to implement in a computer to do all this. So, you know, eigenvalue computations, you know, you don't really want to do them at every stress integration point if you can avoid it. So if you need to use these invariants to develop a constituent model, you don't want to first do the eigenvalue decomposition to find the invariants to use this equation on the right-hand side. You know, what you'd more likely do is just do this, you know, the trace is easy to find, right? Do this tensor contraction and subtract 1/2 the trace squared, right? So, so the I3 is the determinant of the stress tensor. By the way, there's nothing special about these invariants related to stress. These are true of any tensor. So the stresses could also be strains. The strains would have 3 invariants, right? Or any second order tensor is going to have these same 3 invariants. So meaning, you know, if you have a second order tensor and you compute these things and you perform a rotation on that tensor and you compute the things on the results, they're always going to be the same. All right. So what's the determinant? What do you think the determinant is in terms of the principal stresses? The product of them, right? So remember, that's an easy thing because, right, if you don't know this, the determinant of any matrix is the product of the eigenvalues. Right? What's the determinant of an upper triangular matrix? Huh? What's the eigenvalues of an upper triangular matrix? You know what I mean, upper triangular? Right, so upper triangular would be a matrix that has entries on the diagonal and above it, right? And all zeros down here. So what are the eigenvalues of a matrix like that? They're the ones on the diagonal. So the determinant is the ones on the diagonal, right? So does anybody know what an LU decomposition is? You can take any matrix. This is just an aside. You can take any matrix and you can do some manipulations and convert it into a lower triangular matrix times an upper triangular matrix. Okay. So since the eigenvalues of the determinant of L is the product of the diagonal, the eigenvalues, right? And there's also an identity that says like the determinant of A is equal to the determinant of L times the determinant of U. Right? If you know any multiplication of matrices, the determinant is the determinant of each of the product of each of the individual components, right? So anyway, this is an aside, but I'm just saying to get to this point. Anybody know how a computer would actually compute the determinant of a very, very large matrix? It's like you have a million by a million matrix. It does that. It does. You think it does that discriminant thing that you learned, like where you take the take the first entry and multiply it by the 999,000 other ones, right? And then the determinant of that guy, and you just keep going. Of course it doesn't, right? It does an LU decomposition, right? First, and then takes the product of the diagonals and multiplies them together. That's how you get the determinant of the big matrix. That's how a computer does. Okay. Last little thing here in the last 2 minutes. We can also take the stress tensor and we can decompose it into something we call the spherical or the hydrostatic part plus a deviatoric part. So we call this the spherical or the hydrostatic or sometimes the dilatational stress. And then this is the deviatoric stress. By the way, sometimes we call the first invariant, we'll say that it's 3 times the pressure. And the reason for that is that because sometimes we say that this thing is the pressure. Right? Notice sigma kk is sigma I. They're the same, right? Sigma kk, if you have a repeated indice, it's a dummy indice and you can replace it with anything. So sigma kk, I can say sigma I, they're identical. Right? So if sigma kk is 3p, then I plug it into this equation and I'd get what I said, 1/3 of that would be p. Okay, and so this is called the pressure. Now this pressure is not, later we're going to learn about pore elasticity and it's going to be a fluid pressure. This is not that pressure. This is the hydrostatic pressure due to mechanical deformations. Okay, and this Sij is the deviatoric stress. That's related to or is a measure of the shear strain in the material. And the reason that this decomposition is useful is particularly when it comes to plasticity modeling. So for instance, if we think about a metal, we assume that metal undergoes isochoric deformation, meaning volume preserving deformations. So in other words, if I take a metal and I squeeze it forever, when I let it go, it's going to spring. When I squeeze it, I mean squeeze it equal and opposite. Apply an equal pressure to all sides. I'm never going to plastically deform it. When I let it go, it's going to spring back right where it was. Okay. Now, a rock won't do that. A rock has pores in it, and you can collapse those pores, and you can't have permanent deformation due to pore collapse in a rock. But in a metal, it's a good assumption to say that it's isochoric, and so all of the plastic behavior is irrespective of the pressure or the hydrostatic component, and we just sort of implement the plasticity model according to the deviatoric stress. And this deviatoric stress has its own invariants. We call them J's. Right? So J1 is actually always equal to 0. J2 is equal to 1/2 Sij, Sij. And J3 is equal to the determinant of S. And as I know we're a little bit over just one last point. I mean, I talked about plasticity. I hope you know what I mean. So when you're undergraduate class and you wrote down a stress strain curve, it always looked like that, right? Linear elastic. Let it go, it goes back to zero, no strain. Well, real materials don't behave that way. Very few do. Particularly a metal, if you continue to strain a metal, you get a stress strain curve that looks something like that. What about a rock? Well, if you go to the lab and you squeeze a rock in a standard test frame and it's unconfined, well, you're going to load it up to some level and it's going to break. And it's going to be linear elastic until it fails. It's going to split, right? However, if you put it in confinement like it is in the earth, and you continue to load it, you continue to strain it, you'll see significant plasticity. And you see this softening effect, and the softening effect comes from pore collapse. Okay.